Today we're going to be talking about converting between complex and polar forms. One direction requires a bit of work and the other direction is quite straightforward and simple. Let's first look at these two forms side by side. Complex form we discussed yesterday, so that's nothing new. Complex form, that's a plus bi. Now your homework assignment, it's going to be similar to yesterday's in that if you didn't or couldn't tell, this comes from Delta Math. I just pull problems from it. It's just easier and for me. And the problems on there, for whatever reason, they don't like to call it complex form. They have a completely different name for it. So when you see this alternative name, just know that they mean complex form. So on the homework, they like to call it a rectangular standard form. So when you see rectangular standard form, they're talking about complex form. That's the only time you'll see it written like that is on the homework. Otherwise, test and quiz, it will say complex form. Polar form is new. Polar form is r times cosine of theta plus I sine of theta. If you remember yesterday's notes, you should recognize a couple pieces here. The r is the modulus, which was the absolute value of the complex number, a plus bi. And the theta we called the argument. So in order to get it into polar form, we're going to have to do both of those things, what we covered in the notes yesterday. We're going to have to take the complex number and find its modulus and its argument in order to convert. That's the one that takes more time to do, more work. That's what we're going to start with. I will only do one of these. So we're going to go complex to polar. Example, convert to polar form. And we are converting 3 plus 3i. Now I'm going to write at the bottom here what the goal is. So again, the goal is r cosine theta plus I sine of theta. So once we find r and the value of theta, we'll be done with the problem. So we can summarize this into 3 steps. First thing, of course, we're going to graph it, get a visual to work with. Now, just thinking ahead, this is right 3, up 3, so we're going to be in the first quadrant. And if you don't want to draw a large coordinate plane to work with, you can kind of cheat a little bit. I'll show you. So it doesn't need to be accurate to size. Again, this is really just an image to work with. It doesn't need to be graphed perfectly to proportion. So again, we're going to go right 3, up 3. So I'm just going to make notches for the 3's on the axes and just go with that. So there's our point. And remember, we're in the complex plane, so this is the real axis and the imaginary axis. Our first goal is to find R. So let's go ahead and graph R. R is the distance from the point to 0. So from the point to the origin. And basically we're just finding the hypotenuse of the triangle. So we're going to need the other two side lengths, which we already have. Let's create the triangle. We drop it to the x-axis. And both sides have a length of 3 because it was right 3 up 3, both positive in this case. And we use our Pythagorean theorem to find R. A squared plus b squared equals c squared. A and b are both 3. And then the c is R. So 3 squared plus 3 squared equals R squared. 3 squared and 3 squared, that's 9. 9 and 9 gives us 18 equals R squared. And then don't forget we are solving for R, not R squared, so we're not done. Don't forget to square root both sides. R is equal to the square root of 18. Now we're not done. If you can simplify a radical, we expect you to. So let's bring back that little topic. The 18 can be simplified, and unfortunately your calculator cannot break this down for you, but you can use the calculator to check the answer once you have it. So depending on who you had last year, depends on how you go about this process. But what I tell my students is to just find two factors of the number, so in this case 18. The most straightforward way to go is to find a perfect square specifically that is a factor of 18. So I'm sure most of you probably think 9 and 2, and that is the more convenient way to break it down. So I'll go with 9 and 2. And I keep the square roots on there when I break it down. And then the 9, which I chose because it's a perfect square, breaks down into 3s. Since the 9 got broken down, I'm going to cross it out. That leaves me with a pair of 3s. And if I make a pair, then 3 itself can come out of the radical. Square root of 3 times itself is 3. And then we have a square root 2 left over. So our new value of R is 3 square root of 2. And then if you're not sure if that's correct, you can always check it in the calculator. Put the before and the after. They should get the same decimal. So that's what I'll do here. Square root of 18 and 3 square root of 2. Same decimal, we're good. So we could go ahead and fill that in the answer if you want to do that. So we know we have 3 square root of 2 for the R value. And then I'll go ahead and set up the rest of it. Now we just need the value of theta, and then we'll be done. Yes.
When we find the value of theta, do we abbreviate it?
Did you say abbreviate?
Well, I've changed it, because like, let's say hypothetically, we'll get cosine of 45. Would that turn to...
I see what you mean. No,
like
don't evaluate. Don't substitute. No.
Okay.
And I'll get to that because that is something that happens often. And it'll be at the very end, but I'll circle back to why you don't do that. Okay, so we found R. Now we have to find theta. Once we find theta, we'll be done. Finding theta, let's draw theta first. So theta is the angle of rotation. We start at 0 and go up to where the angle ends. There it is. Alpha, we draw from the x-axis, the real axis, up to where our angle ends. There's our alpha. And for this problem, you'll notice they're both inside the triangle. They're both in quadrant 1. This is the most convenient way we can have it set up. And then to find alpha, we use tangent of alpha equals O over A. And we do this because we always know O and A in these problems. R is always the H, the hypotenuse. And then the alpha, or sorry, yeah, the vertical is O and the horizontal is A. A always goes on the horizontal, which conveniently touches alpha, which is also the Greek letter for A. Filling in, I have tangent of alpha equals, O and A are both 3. 3 over 3, which is conveniently 1. And then to solve for alpha, remember we have to use the inverse tangent to remove it from alpha. So inverse tangent of 1. And then we can use the calculator to get that answer. And yes, alpha is 45 degrees. Remember, the goal is to find theta, so alpha is just a stepping stone to get there. We're in the first quadrant. And in quadrant 1, the rule is that theta equals alpha. If you remember those rules that we wrote down yesterday, the rules we've been using for about half the year now. So since alpha is 45, theta is also 45 degrees. So then we can fill in for after cosine and sine 45, since that is the value of theta. This is our answer. Questions on the work, getting to the answer. So back to the question that Devin asked earlier. This is polar form right here, this exact setup. So if you evaluate, if you replace sine and cosine with the values they are equal to, you're taking it out of polar form, because polar form has to have the sine and cosine in it. So the hardest part for you guys is remembering, once you put the pieces, the numbers where they go, leave it alone. That's your answer. That's polar form. All right, let's do the easier way, polar back to complex.
This would be the final answer.
Yep, that's the final answer.
No calculator.
No calculator. Polar to complex. I'll do 2 examples. Convert to complex form. Find the exact answers. And when that says exact, that's your hint that you're going to use the unit circle. Because if you just type it into your calculator, you're not going to get exact, you're going to get a decimal. The unit circle, as always, will be provided for you on the test. Okay, let's write out the problem. Our number here is 3 cosine of 225 plus I sine of 225. All you're going to do essentially is substitute the sine and cosine values and then do the algebra that is required. So first thing I'm going to do is replace cosine and sine with what they're equal to. So we have 3 times and then cosine of 225. 225 cosine, the x value is negative rad 2 over 2. Plus I, and sine is also the same value at 225. Negative rad 2 over 2. So that was step 1, substitute. I'm going to write it again before I do the next step. Now this time when I write it, I'm going to go ahead and flip these around. When you have a number here, you attach the I at the end. So we have negative rad 2 over 2. Then just put the I on the outside after it. Follow the algebra. We have a 3 on the outside. We can distribute it. Step 2, distribute. Now remember, when you're multiplying that 3 in there, you're multiplying by 3 over 1. And when you multiply fractions, it's just straight across. So all you're going to end up doing is put a 3 on the top of both of those fractions. We have negative 3 rad 2 over 2. And then plus minus, I'm just going to turn this into a minus. 3 rad 2 over 2I. And we can't combine these because this has an I, this one does not. Also, reminder, the goal is to get it into complex form. And complex form is A plus BI, which is what we have here. We have the A, the real part, and BI, the imaginary part. So we are done. This is our answer. So that was step 3. Answer, reduce if possible. And we will be able to reduce the next problem. Questions on converting polar to complex before I do my final example?
The 3 always goes on the outside.
Yes, that's the R value.
Okay.
Okay, example 2. Our number is 4 cosine of 7 pi over 6 plus I sine of 7 pi over 6. So this number is currently in polar form. Once I substitute and do all that, I'm taking it out of polar form and putting it into complex form, which is what I want to do this time. First we replace 7 pi over 6. That is in the third quadrant right here. Cosine is negative rad 3 over 2. And then sine is negative 1/2. I'll rewrite it before I distribute. And in the process, I'll flip around the negative 1/2 and the I. And we have the same scenario of what happened last time, where we have a plus, minus, or plus a negative. So I'm going to go ahead and write this as minus 1/2 I. Then I'll distribute. Again, you're basically just going to put a 4 on the top, multiply on the top. Negative 4 rad 3 over 2 minus 4 over 2I. And this time I can reduce, so I will. Negative 4 over 2, that'll just become negative 2 rad 3 minus 4 over 2, so we have 2I. Again, this is in A plus BI form. That is our complex number. We are done.